My name's Samir, and I'm a product manager here at Maplesoft. Today, we're going to spend some time talking about what our electrical engineers do with math software. We'll discuss the tools and features in Maple for electrical engineers, and we'll walk through some applications. And it's the latter point, the applications, that I get really excited about, real-world analysis using tools like Maple. Now, if you go to the Maple Application Center on our website, the address is here, you'll find thousands of applications and worksheets across many domains. There are many electrical engineering examples, and we're going to demonstrate a few of these in a few minutes. There's a lot there, and I do encourage you to spend some time browsing the material that's available. First of all, the bigger picture. Now, Maple is a general purpose tool for math, modeling, simulation, programming, visualization, and data analysis. It is a broad, deep, numeric and symbolic math engine. It also understands units. Units pass from parameter definitions through to solvers, straight all the way through to the final results. You can analyze many different types of data, and there are many examples and applications for you to explore. The interface is one of Maple's biggest features. A Maple document is a rich environment for math and documentation. You can include equations in natural math notation. You can have fully formatted rich text, just like a word processing environment. You can have tables, you can have images, animations, and many other elements. This means you can capture the assumptions, background information, as well as calculations. I'd also like to highlight the fidelity and quality of Maple's plots. You can produce some very visually impactful plots and charts. You can finesse the look and feel of those plots, right down to the precise color grading of the color range on a spectrogram. The plots and visualizations are in line in the worksheet. That gives you a close connection between the algorithm or the calculations you're doing and the results. And these plots can also be exported to external image formats such as SVG, PNG, and more. So right now, let's just jump into Maple and discuss a few Maple applications. And everything I show you today is available on the Maple Application Center. We'll go through maybe about 5 or 6 of these. Let's start off with this one. So, analog circuits can be modeled with transfer functions, and this involves a lot of algebraic manipulation. If you're doing this by hand on paper, you need to concentrate. You need to sit down at a desk with a strong cup of coffee, paper, and a pencil, and you need to apply yourself, and that's not always easy. And if you're doing anything by hand, the scope for error is enormous. Maple helps you manipulate transfer functions. You can rearrange transfer functions and nodal equations. You can simplify those equations to the most concise form. You can identify unknown parameters or symbolic names in a set of transfer functions. You can substitute in numeric values in for those names. There are also tools to convert netlist-like descriptions of circuits into transfer functions, generate phase and magnitude plots, and more. So let's look at this application. First of all, let's just see what's in here. We have a title, a description, and a diagram of the problem. This was simply copied and pasted in from another application. Looks like I have some parameters here, obviously some resistances and some capacitances. I have a support function here, and then I do my math here. Looks like I'm manipulating some transfer functions. I'm adding in some non-ideality effects, and I generate a visualization at the bottom. Okay, let's just execute this entire worksheet. And let's go through this in a bit more detail. Okay, first of all, we have this bit of the circuit. We have a resistor Rin connected in parallel with another resistor R1 and capacitor C1. Okay, so this can be modeled with transfer functions. We just need to connect both in parallel, and we do that here. So earlier in this worksheet I had this function. This just connects, models the effect of transfer functions connected in parallel. So I have my resistor Rin connected in parallel with my other resistor R1 and the effect of this capacitor, and that gives me this. That's looking a bit unwieldy. It's not in its simplest possible form. What I can do is use Maple's symbolic math tools to simplify this equation. A couple of ways I can do that, but I like using the context panel. Let me just expand this panel on the right-hand side. This just gives me access to a number of context-sensitive math options. Because Maple recognizes that this is a transfer function, a rational polynomial in S, I have a dynamic systems menu which allows me to create various control plots such as a magnitude and a phase plot. But what I'm going to do is select this option, simplify, and let's simplify this equation, and we get this. Maple inserts the simplify command together with a reference to equation label 2.1. This thing here. This is simply the command I could have typed in, but I prefer using the context panel to do these things. It's so much quicker, so much simpler. Okay, so that's simplified this equation. Then if I look at what I'm doing here, I'm modeling the effects of this part of the circuit, so RF, R2, C2, and C3, and developing the combined transfer function of that set of components, and then simplifying that equation, adding in some non-ideality, and if I scroll down to the very bottom, I get the non-ideal amplifier gain. Then I can feed that final result to these commands, which give me a phase plot. So here in this phase plot, I have the phase of the non-ideal system and the ideal system. Now, if I right-click on this plot, I can actually export it to an external file, so SVG format. This is something that we added recently. If you export a Maple plot in SVG format, it's a vector format, so even if you zoom in to the exported plot, the text, the lines still remain sharp and crisp. Now, if I change a parameter value at the top, let's change this resistance, and I hit this button, that change cascades down the length of my Maple worksheet, and all my plots, dependencies, and results update to reflect the new parameter value. Let's just delete this. Now, I had purely numeric parameters in here. What happens if I change some of these parameters to unknown symbolic names? Let's just go with those. So let me just execute these definitions, and let's see what we get. So let's update this equation. So as soon as I hit enter, Maple gives me the updated transfer function, but it substitutes in these symbolic names for the parameter values. Same with this, this. And right at the very bottom, I get the amplifier gain. Now, this is pretty long and unwieldy, and again, I'm sure you'd agree, if I was trying to derive this by hand with symbolic names for parameter values, I'd probably make an error. It's much easier to let Maple do the heavy lifting. So, this is one approach to modeling this circuit. There is another approach. There's a free package on our website on the application center called Syrup. This allows you to convert a netlist-like description of an electrical circuit into transfer function. That package is called Syrup. It was developed by one of our users. So this is the netlist-like description of this circuit. But what I can do is convert that description to a symbolic transfer function. And then once I've got this, I can manipulate this equation, this transfer function, as I would do any other transfer function within Maple. I know this is a very popular add-on for electrical engineers, and it's available free on our website. You can also create interfaces that sit on top of a Maple application. And this is a version of the first application I showed you, but instead of seeing the equations and the parameter definitions, I simply have slider values which allow me to change parameter values. There are text boxes as well, which allow me to change values. And you'll probably see this plot changing as I move these sliders. You can actually deploy this application free of charge. We have something called the Maple Player. It's a runtime version of Maple. It's a free download on our website. So you can just load this application straight into the Maple Player, and you can twiddle about with sliders, dials, gauges, and widgets. And you can also deploy this free of charge to the cloud as well with an in-product tool called the Maple Cloud. And that just allows you to interact with this application with nothing more than a web browser. Let's move on to the next application. And let's try this one. I do like this one. Okay, so let's talk about equivalent circuit models and symbolic math. So an equivalent circuit is a theoretical circuit that gives you the bulk electrical characteristics of a given circuit. Often you derive an equivalent circuit model because it simplifies calculations, and it's the most simplest form of a complex circuit that helps you analyze the system. For example, the lithium-ion batteries in electrical vehicles are often analyzed using equivalent circuit models. Now, with Maple, you can use Maple symbolic math tools to turn equivalent circuit models into analytical equations, and that's exactly what I've done here. So this, for example, is an equivalent circuit model of a MOSFET. So this is the simplified schematic of the MOSFET, and this is the equivalent circuit model. And here are the basic mathematical relationships that we're manipulating. I'm not going to go into this in too much detail, but basically I derive several differential equations which I can solve analytically using Maple's dsolve function. And this is the resulting equation. And right at the bottom, you can see that I've derived the gate voltage for the MOSFET. So once you've got this equation, you can perform parameter sweeps, optimizations, plot it, and much more. Let's talk about worst case circuit analysis and extreme value analysis. Let's start off with this one. Now we have many customers who use Maple for worst case circuit analysis, and there are two approaches I'm going to show you. In this worksheet, we perform worst case analysis using Monte Carlo simulation. So this is our circuit model. It's a photodiode model. And here are the parameter values. My resistors, my voltage, and these are the mean values for the parameters, and I have a variance. So all of the parameters are normally distributed with a mean and a variance. This is a Maple procedure. I've written it straight into the worksheet, although there are several other ways I could have written this procedure, but it gives me the output voltage, this thing here, given values for all of these parameters. Using Maple's statistical functionality, I can generate 1,000 random samples for each parameter. I supply its mean and variance. Once I have those parameter values, I can put all of those back into my procedure and calculate 1,000 values of the output voltage. Let me just execute this worksheet and I'll show you some of the intermediate values. So you can see that I've bookended this line with a colon. If I remove the bookend, remove the colon and replace it with the semicolon and I re-execute this, I see this. So these are the first 100 values of the 1,000 random samples that Maple has generated. If I remove the colon from this and hit enter, these are the 1,000 values of the output voltage Maple has generated. Now, once I've got this vector of output voltages, I can calculate the mean and standard deviation of the results. And then I can plot a histogram using the 2 sigma limits of the output voltage. So 95% of the observations lie between 2 standard deviations of the mean for a normal distribution. Though I can say with some certainty that the majority of the readings will be between these 2 values. So this application uses Maple's tools for sampling probability distributions, element-wise calculations for fast numeric evaluation, and generating histograms and statistical analysis. Let me show you another approach for the same problem. Again, it's the same circuit. It's the photodiode circuit, but this time, instead of a mean and a variance for all the parameter values, I have a value and a percentage tolerance. So this resistor has a nominal value of 900 ohms plus or minus 0.02%. The actual value can be between the nominal value and plus or minus the tolerance. Now, I want to calculate the voltage for every permutation of parameter values at either end of the tolerance. There are 9 parameters. That means there's 2 to the power 9, or I think 512 individual combinations. Again, I have a procedure that calculates the output voltage. I then have 2 lists of data, the parameter values, the nominal values, and the tolerances. And then I use Maple's functionality to calculate the output voltage for every permutation of extreme tolerance values. And that's what I have here. And then I can calculate the minimum and maximum voltages. And these are my worst cases. Now, this uses Maple's tools for generating permutations of parameters, element-wise calculations, and statistical analysis. On to the next application, and we'll do this one quickly. Let's look at stub matching. So electrical engineers often need to match load to the impedance of a transmission line, and this is known as stub matching, and it involves numerically solving nonlinear equations. It could be a single nonlinear equation, or it could be a group of nonlinear equations, and that requires strong numerical solvers. Now, traditionally this was done using tools like Smith charts, but it's much easier to do this in Maple using Maple's fsolve function. Again, I have my parameter values, but this time I have units associated with the parameter values. I have a couple of wavelengths as well, and again I'm using units. This is my circuit equation. And this call to fsolve calculates the location and length of the stub. And the results pop out with units as well. Now, using Maple's functionality, I could rescale the results to another consistent set of units. So the location and length are given in meters. I could convert it to inches and yards if I wanted to. So this demonstrates Maple can carry units from parameter definitions through to analysis and the final results of your analysis as well. Let's run through the next one quickly as well. Let's look at this one. So you can produce some pretty attractive design documents using Maple, and that's what many of our customers do. Now, we have some users who use Maple for antenna and radar design, and they use Maple primarily because of its ability to create executable design documents that capture both the math, the calculations, and the documentation. So they do things like this. They have images. If you look at what I've done here, my calculations aren't all in a single row. They're in columns. And what I can do is reveal some of the underlying table structure with the context panel. So this is simply a table with 2 rows and 2 columns, and I put parameter values and text in each of these cells. Let's remove the table borders again. I then have a further set of equations. I then have a couple of plots. In this instance, I'm calculating the E-plane radiation pattern of this antenna. And again, I can export this plot to an external file using Maple's context menus. Now, once you've created a design document like this, you can export it to a PDF. Now, if you go to Export As, that allows you to export this document straight to a PDF file. It's not something I'm going to do right now, but if you go to the File Print Preview menu, this shows you what the PDF would look like. It's pretty nice and presentable. Now, for the final application, I think I'll show you this. Now, signal processing is an important part of any electrical engineer's toolkit, and Maple offers you many tools for analyzing and manipulating signals, and indeed other kinds of data such as images, audio files, and more. I'm not going to go through all of the detail, but there's a whole spectrum of functionality for spectral analysis, upsampling and downsampling systems, signals, generating periodograms, importing, exporting data, and so on. In this specific application, I'm applying FIR and IIR filters to audio files. Start off by importing an audio file. Here, Maple summarizes the audio file by telling me the sampling rate, the length, the number of channels, and so on. I can then use some of Maple's built-in functionality to analyze the frequency contents over time with a spectrogram. And here I also generate a periodogram as well. And let's say I want to do some filtering. Let's say I want to apply a Butterworth filter, an IR filter. Start off with cutoff frequency for my high-pass filter. I generate the filter taps. I then apply the filter taps to my data. And then I replot the spectrogram and the periodogram. And you can see a difference. There's a sharp cutoff at about 1 kilohertz, 1000 hertz. And that's more evident in the periodogram. Now, if I change this to 3000 hertz, and let's update this document, we'll see what effect that change has on the post-filtering spectrogram and periodogram. And there we go, you can see another dramatic change there. Similarly, I can generate an FIR filter, a bandpass filter, apply it to my signal, and again, this is the effect on the spectrogram and periodogram. Now, there are many other signal processing tools within Maple, but I'm not going to go into that in any great detail. So that was everything I wanted to show you today. All the worksheets I presented and more are on the Application Center for you to download.